Thanks for the introduction. I'm Tom from the Software Architecture Group in Potsdam, and our group deals with all sorts of things around programming and programming architectures.
Yeah. Sorry, can you start again? We just lost the internet for a second.
Oops. All right. Is that on my end or on your end? Do you know?
We can hear you now.
Okay. Okay. Let's cross fingers that it stays stable.
Yeah, we can also see your slides.
Say that again, please.
Yeah, we can see your slides. Can you probably make it full screen?
Can I though? Yeah, I can indeed. All right, cool. So yeah, Tom from the Software Architecture Group in Potsdam. These are the sort of topics we deal with, starting from virtual machines, going about programming language to development tools. But as the title suggests, this particular talk will be sort of bridging across those two. So we'll be looking at how our goal to build a VR live programming system informed, first of all, a communication architecture, and second, a programming model, leading to that mix of technologies that we have in the title. So I'm hoping you'll take maybe a different look on a technology you already know, or maybe a new look on a technology you hadn't already known away from this talk, and yeah, maybe get inspired by it. I don't know if this is viable, but if it makes sense, please feel free to try and ask questions during the talk. I'm just gonna backtrack by the time the question arrives here, and also can't see the air meet. So if there's something coming up, would be great if you could just unmute and let me know about it. Cool. So with that out of the way, let's see what we have. So briefly on the motivation here, this VR development thing. So if you've ever used VR, you probably know there's like this whole hardware part about it, and the more interesting question is maybe if you've ever developed for VR, because that experience in many ways is not quite ideal, because, well, you're sitting on your laptop, you're typing, you want to test a change, you have to put on your headset, you have to find the controllers while having the headset on and the tracking is not quite right. You have to then actually go in VR to that physical location where you want to test it, try it out, and then if it doesn't work, do the whole shenanigans back, make sure it's securely on your desk, change, sit down, program again. So this is not necessarily what the ideal feedback loop would look like. So what we were trying to do is bring those two things together. Somehow, open question right now, make VR work with a live programming environment for this very fast feedback loop. All right, I'm just hearing that maybe it makes sense to turn my video off for better connection. So I'm just gonna try that. All right, let's see if that helps at all. Moving on. So this is the starting point. We want to combine a live programming system that supports fast feedback loops with a VR-compatible graphics stack. That was sort of our mission to reach this idea, or rather to be able to work on this idea of a VR programming environment. And as I said, this talk is going to be on that journey mostly. So we're going to look at a couple of aspects here: communication, the programming model. We're going to look at this React part, and there will also be a demo with some aspects around live programming. So the first piece is Godot. If you've never heard of it, it's an open source game engine with support for VR and AR rendering, of course, but also all these other things that you might expect in a modern game, such as physics, audio, all sorts of graphical tools. You can see a screenshot here in the lower right. The alternative, if you just think about this problem in more general terms, might have been a rendering framework without any sort of engine, but there was very little expertise among the target audience that was supposed to work with this, whereas Godot was a rather familiar piece of software. So we would really like to use Godot as our basis here. The way that Godot is typically programmed is in an imperative object-oriented style, where you have node subclasses that are composed into a scene tree. You can kind of see that here on the lower left, where you have this kinematic body containing all sorts of other nodes. And node subclasses may have a process method that is called every frame if it is defined, which would be typically the 60 per 90 frames per second, whatever exactly your target system is. So some typical Godot code, just as an idea, looks like this. You have this process function, which might have a vector for moving. And if there is an action currently pressed, such as the jump, which might be bound to the space key, you set its Y component. And finally, you do this move and collide function of Godot to move the player forward by whatever the move vector imperatively got assigned to during this tick. So that's the Godot part about it. The second one, the live programming system that we settled on using as a basis here is Squeak Smalltalk, which is self-sustaining and designed for live programming in mind. And just to illustrate that real quick, I'm going to briefly switch over to Squeak itself. So let's just quickly create a demo morph here. So morphs in Squeak are this sort of unit of graphical representation. So if I'm just gonna do a little script in here in the step function, which is Squeak's process, if you will, and open that here, we can see that this cube, probably can't see it right now, it's very slowly moving down, and if I just reduce the time at which does that, it starts moving a little quicker. And of course, I can change this now live, and it will, for example, change direction. Oops, not quite what we wanted. Now it's underneath the window. Yep, there it is now moving diagonally. And you can see this is working rather well. I also have these cool direct manipulation tools, which I can use to manipulate the system as it is working. And I can also inspect its properties. So this bounce property keeps changing as the little rectangle is moving. I'm trying to catch it here again. But there's one aspect that is not quite as live, which I'm now mentioning because it will become later relevant again. That is if I change the past, namely the initialize of that cube. So if I said I would have liked it to be red, nothing is going to happen because this one already exists. So I'm going to have to delete this or reconcile the state in another way. But if I create a new one, this is going to have run its constructor, the initialize here, and appear in red as we would expect it to be. So these live programming systems allow you this very fast feedback loop that typically help you understand your problem as you're going. And yes, because of the many facilities that Squeak offer to support this sort of feedback and self-sustaining idea, we thought it would be a great basis for this VR programming system we had in mind. So that was our mission, to combine the Squeak Smalltalk live programming system with the Godot game engine. There were a couple of requirements we had in mind, namely, of course, that it provides that interactive frame rate that VR requires, around 90 frames per second, that it is rather simple to deploy and supports all our target operating systems, in this case, quite a few here. Now, the challenge is that Squeak is not necessarily designed to be embedded. It comes with its own front end, as you can see. And we also wanted to keep this front end for purposes of bootstrapping because it's allowed us to essentially work in the Squeak IDE while this VR system was running. So what we get is actually two main loops that competing for attention, I suppose. We have that game loop running in Godot and also the Squeak windowing system with its own user interface running in parallel. So how can we make those two talk? Well, the approaches that come to our mind were FFI and IPC. And actually, in the spirit of the previous talk, we had also considered GraalVM actually using truffle Squeak and compiling Godot to LLVM. But for the moment, that remains to be a thought experiment. We haven't investigated compiling Godot just yet in that manner. So looking at that first idea, if you were to use FFI, the cool thing would be that it would be very easy to use Godot's functionality from Squeak because essentially it's just a foreign function interface call from Squeak to Godot. However, there's one major problem. We are having to synchronize every single call because we have these two main loops. So because Godot cannot just synchronously own a thread on Squeak's end, we sort of have to queue messages on Squeak's end. Squeak has to poll for them, process them, and then tell Godot, hey, I'm done, you can continue. So this overhead of synchronization actually cost us a lot of performance here. And in addition to this, it is rather annoying, at least in our experiments so far, to import and update that libsqueak SO that you see here and bundle it with Godot also as a native plugin. Yeah. So the second approach that we thought about was using TCP, as you've already seen in the title. So, and for one form of inter-process communication. The cool thing here is in particular that it's extremely simple to deploy. We have an unchanged Godot, we have an unchanged Squeak, and everything we need is one common port to be open on both ends to exchange data. We still have that same synchronization issue, this time more explicit because of the actual barrier between the two. And it might even be slower. In practice, we didn't notice that much of a difference, but we also didn't go all the way to optimize every single part about it. So you might be wondering why no UDP, which is typically used in games. Arguably, this is, or at least in my experience, used mainly to provide different classes of service, reliable and unreliable, which we didn't really need. We only needed reliable communication. So that kind of ruled out UDP because we would essentially just be implementing TCP on top of it, as games usually do for their reliable service class. And the other aspect would be wondering why we didn't decide to use pipes for this inter-process communication. For one, well, they're less portable, looking at Windows mostly. And another very cool aspect here is actually that TCP allows us to communicate between the two processes, even though they are on different devices. This, for one, allows us to communicate with standalone headsets that have their own computer running on the system and Squeak running on a laptop. So the Oculus Quest or the Pico have a proper computer running Android on the headset on which we can launch Godot, connect likely via cable for the best experience to our Squeak system running on a laptop and communicate between the two, which is obviously quite cool and would have been slightly more difficult to do otherwise. All right, so is this our solution here? Well, almost. We have a robust architecture that is simple to deploy. We have access to all the desired functionality, but we have this barrier here in the middle that we have to cross every time. And in our measurements, it took around 0.5 milliseconds per message to go from Godot to Squeak and back. Since we want to have that 90 FPS, that means that we have around 11 milliseconds per frame, but in the sort of rendering scenarios we have, 8 of those are already taken by Godot, meaning, well, we're left with around 3 milliseconds, which is not quite perfect just yet, because, well, it means we can only have up to 6 messages per frame. So this sort of imperative style of programming is definitely not viable here because, well, everything we do will incur those 0.5 milliseconds of message exchanging. So that brings us to the second part that we considered, the programming model. So that's not quite as pretty. We have this constraint of 6 calls per frame. And if you consider this little piece of code here, so I'm just going to quickly fix. We have actually 3 calls going on here, right? We instantiate that cube on the Godot side, we set its color on the Godot side, we set its position on the Godot side, and we haven't even added it to the tree, and yet we've exhausted 50% of our frame budget. So there's one observation that sort of saves this whole approach, namely that the size of the calls is almost irrelevant. It's really this fixed synchronization step that occurs per call that is this high overhead. So intuitively, a first solution might be to batch messages, collect all of those, make a single remote procedure call with all of those messages sort of described, and well, send them off the Godot to run. However, there's one major challenge if we approach this from an imperative point of view, because imperative code tends to rely on its own side effects to already have taken place. One simple example is here. We want to advance the position of the cube for something, and then we read the position of the cube and make a distance check. You could argue that maybe this isn't as relevant here, but still, it's a very clear data dependency, right? Here's a write, then there's a read here. There's some workarounds maybe. For example, we could only batch read accesses, or we could make batching explicit in the sense that the user can tell us, okay, you can batch these calls, but here I want a barrier where everything needs to be written. But all of these definitely don't make it easier to program against this model, and also make it slightly more difficult for the programmer to understand what the constraints are, and when performance suddenly degrades because there's, for example, a very write-heavy function, and our system wasn't informed that these can don't affect one another. So we were looking for alternatives, and what we turned to was the declarative route. Namely, we wanted to look at a programming model that is designed to batch side effects, for example, React, as you've seen in the title. So this type of programming model forbids, or at least makes it very difficult to depend on side effects to already have taken place. How does it do that? Well, I've just tried to kind of model. It's the same example here. We have this local or app state setting some type of position, and we have this render function, which is continuously repeated, that kind of declares the dependencies on how the display should be based on the state. So you can really think of this render function as a function of the state that produces the view, sort of in the Elm architecture, or React, of course, if you're familiar with those. So we can see here, these read and write the local state, that is the app state up here. So let's just quickly walk through this. We instantiate this cube, we set its column, we set the position to the position that is in our local state. And when this key press occurs, we set its position by advancing it around a certain increment. But all of this occurs on this local state. Now, how would this distance check happen? Well, it can't actually, because the data is not in the local state, this data of where the other thing is, at least the way we've modeled it here. We could put it there and then it's all good again, but the very way this is designed encourages to think about a more event-driven manner. So this is also something we could have done in the imperative way, but the imperative way does not necessarily encourage it to do, but rather it encourages you to just place these calls and be happy with this, because that tends to also be the most performant way of doing these sort of things. So the adapted solution might look like this, that you put these sort of area detectors that Godot provides us with around that cube, and give it the same radius that your distance would have been. And when that area gets entered by our player object, we perform the side effect that we wanted to have done otherwise in an imperative manner. So this brings us to sort of the overview of our architecture, which we dubbed Grease for Godot, React, Squeak. And in ReactJS terms, if you're familiar with it, Grease is essentially a host config to the ReactJS runtime, which is a re-implementation of ReactJS in Smalltalk, which is essentially comparable to the same thing that React Native would do, except we do it on two different processes entirely, not just on two different ecosystems, if you will. So what's happening? Well, we have Grease on the Smalltalk side communicating with ReactJS to produce messages, send them over to TCP. Godot has a Grease part running as well, renders the things that we inform it to, and then does the XR shenanigans if it needs to. So the primary goal of involving React here was to reduce communication, but along the way we also learned or realized again that it actually has quite good potential to support a live programming loop. So just to show that here, again, the sort of idea, this is how it works in the web for ReactJS. You have your app, which produces this virtual DOM, a description of what your view should look like with all concrete values. This in turn is turned into a concrete DOM, the doctorate open, so basically your web page, which has event listeners installed if you need them. When those events are triggered, they inform the React app. The React app produces a new virtual DOM, which in turn gets turned into the real DOM. So slightly different view for our thing, but essentially the same idea. We have our ReactJS app. We have a virtual scene tree for Godot. We have this TCP barrier crossing to the Godot side, where the actual Godot scene tree is produced. Godot informs us of events, and the React app can update. All right, so yeah, let's see that in action. I'm just gonna create a new React component here. And to get that started, we're just gonna put a render method here and return a GD camera, which is all we need to do in order for Godot to start doing things. So, well, that is not what I want to. Okay, yeah, that's better. All right. Well, now here is essentially a sort of kernel for Godot's rendering system. That's 500 lines of Godot code, and that is all that is needed to facilitate the sort of rendering side on the Godot end. So this little Godot game, I suppose, is what would be running on your deployed executable, for example, on the Oculus Quest or any other VR device, and will communicate with your running Squeak. So let's do just that. Demo component start listener, which will start the TCP server on the Squeak end. And if we now launch Godot, you can see that indeed we have a 3D scene running. Of course, we don't know if that's the actual scene, so let's put some other stuff in here. Cube of size, let's make it 0.3 in red. And if we save that, nothing happens just yet. But we can send it back a bit, by -2, for example. And there you go, there's that cube. So what actually happened here? We can look at that by toggling this little debug communication toggle. And now, if we restart the game, you can see that there's a whole bunch of things being communicated. What is it actually? Well, it's sort of the diff from what we have previously to what we have now. You can see lots of these add messages for the different parts of our scene. So this cube visual is also just two different Godot nodes being composed here. So if I now go in and change this to a different number, the position, you can see that there's an update call, only an update call occurring for that new position. So if I just put it back down again, you can see now it's here, and we have that update call with -13. So, yep, exactly. Let me check my notes. All right. So with this, in essence, we get the sort of communication good and going, where we have Godot on one side and Squeak on the other, working in tandem to one produce and render this. To produce the scene and render the scene on the other side. All right. So as I said, there's actually a bunch of cool things we can do about live programming. You've already kind of seen how this system refreshed sort of live without me having to restart it, but we can also make this more explicit. So I'm going to introduce a variable here and put that in the, call this y. This is essentially just the number 0 that I'm storing here now. Let's bring this guy a little bit closer again. All right. And we want to create a timer. Exactly. So let's say every 0.01 seconds, we're gonna change this y coordinate to a new value, namely to, I need to block here, time millisecond clock times 0.01, sign to that, and 0.1. All right. So now begins the debugging. Oh yeah, of course, we're not using the number yet, so nothing is happening. And now you see what happens when I do mistakes. You get a debugger, so the option to investigate it further to see what actually happened. But in this case, I'm already kind of aware what I did, because unlike React, we have these explicit getters that we need to place. So on errors, we don't crash entirely. We just suspend rendering and allow us to recover and resume from it. So that's already cool. We have the system going here, but we can still make it a little bit cooler. So you can see here now what is actually happening behind the scene. That's the entire communication, right? On every 0.01 second, a timer will fire from Godot, will prompt us to do something, and in response, we update the timer. Okay, so that's not as interesting anymore, so let's disable that one for a moment. What's kind of cool about this system now is that on every single recompile of a Squeak method, this is gonna change as well. So if I'm just gonna change my system here to recompile on every single change, you can see now as I change these values, I get immediate feedback of what might be a good value and what might not be. Just imagine changing these every time, or restarting the app every time to find these sort of values is obviously quite cumbersome in comparison, right? So yeah. Now this is obviously quite a simple example, but we can also make things a little more difficult, or rather, we can obviously make more complicated things here as well. I'm just going to show you briefly another little demo that we cooked up of like a little car racing game with a top-down view. And again, what's kind of cool about this is that when I realized that my camera is inadequately positioned, it's really easy for me to just go in, change the compile mode, and then finally I can literally just sort of slide around these camera values until I find something that sort of encompasses the game space more accurately. And in this manner, it's sort of like a direct manipulation interface, just that I'm directly interacting with the code. And as such, it is also persisted, not just in the live system, as it would have been in Squeak, but really also as part of the code that is actually going to be run. All right, so let's return to the slides at this point. So this we've just seen, it's essentially just a visualization of what we just saw. And just to like wrap this up, I want to like formalize some of those ideas, or at least give you a better intuition maybe. We've seen this rendering loop. And what happens in particular is that the really cool thing here is that not just state changes cause these update functions to propagate, but as you've seen, code changes do as well, and they're handled exactly the same manner, because to Godot, or rather to the ReactJS system, or React in general, this is just a different virtual scene tree that is being produced, that it diffs to the previous scene tree, and then applies whatever change it might have been. So really, we didn't have to do anything to support this sort of live reloading loop, because, well, Squeak instantly updates methods. So that's part number one. And part number two is that the React system just diffs the two versions that are being produced and creates the minimal update between the two to make the change go live. Now you might be wondering about state, which is a slightly more complicated topic. In brief, we try to preserve state whenever possible, and the only cases where we sort of have to fall back to a discarding state is when you change the order or structure of these little state containers that you just saw. ReactJS also has some more complicated heuristics here to even preserve those as structure changes. But yeah, I'm not going to go into too much detail here. So you've seen at least one instance of me doing a mistake. And the cool thing here again is that these errors are not fatal, at least in almost all cases where you actually would do errors, namely in those view functions or maybe a callback. Instead, what they do is that when an error occurs in the view, our ReactJS system will suspend rendering, will no longer react to events, and wait for you to do any code change, hoping that whatever you changed might have addressed the error. Then it will try rendering again. If the error comes again, well, we suspend and wait for you to fix it again until, well, hopefully you got it figured out. So in addition to this, because obviously, as I just said, we suspend rendering. And that means if you're in this VR development environment, suddenly your entire development environment stops working, which is not quite what you want, most likely. So ReactJS has this error boundary concept, which we also incorporate, which means that a view subtree is guarded by sort of this try-catch statement. So if an error occurs here, this part of the tree is suspended, but for example, our VR development environment, which acts elsewhere, is still safe. Now, what happens if there's no error boundary, which is also the thing that we've kept seeing in the demo? The error bubbles up to the root of the tree, and we have to go into Squeak to fix the error. This is actually also pretty cool, though, because we have the ability to keep the system running. We can recover from our VR development environment crashing fatally by switching to this bootstrapping system, fixing the error, and resuming with the same state that we had previously, unless we corrupted the state, of course. In which case, well, it's either going to be patching the state or restarting whatever part of the environment crashed. So maybe a brief word on performance. We looked at a couple of scenarios, and the worst case would be where every single component changes every frame, and we can handle around 500 of these in terms of our communication structure. And the best case, which is fortunately also how most UIs behave, is that you have some objects that change frequently and a whole bunch of others that are static, and then we can handle 10,000 plus, which is the largest that I tested. Because if you actually do spawn 10,000 objects at once, the startup is going to be very slow, but afterwards you're fine. So yeah, just to wrap up, this TCP idea allowed us to have a very loose connection between our components, which was making our deployment a whole lot easier and allowed us to work across devices. It also gave us this great bootstrapping process where you had the Squeak IDE hosting the VR IDE. We had this idea of changing the programming model, which replaced these implicit or even explicit assumptions that you as the program had to keep in mind with constraints that in some parts limited you, but also pushed you towards this architecture that was better supported for our use cases. So, for example, event-driven patterns. Considering React itself, well, for one, it helped us reduce communication for this use case, and it was also great for live programming in many ways. We've seen initialization code can be updated. We have a solid model for error recovery and these sort of things. However, it also pushes this unfamiliar mentality, especially if you come from this background of live programming and direct manipulation, because you don't really have that anymore. In React, the code is the truth and only the code. Everything else is just derived from the code and as such considered a side effect. You can't really open a debugger on a thing and expect it to still be there in the next frame, because it does not really have this identity and permanence idea here if the code changes underneath its feet, so to say. And the other thing is really that you no longer have this mentality of, let's put this cube as my button here, which you would usually do in this sort of object-oriented system, but rather you think about what's the data in my domain and how do I want to shape it to appear in the view, which also a lot of the people who started out with this framework initially struggled with. Yeah, about performance already talked. So yeah, just skipping over this here real quick, there are some things we want to still improve on. And one part that we're really excited about is actually multi-user scenarios, because we've already noticed this combination of Squeak and VR working in tandem actually encourages you to pair program on the computer and VR in parallel, allowing this sort of interesting feedback loop of testing live as you do these changes. And we're even considering supporting multiple VR users, but yeah, that's definitely an outlook at this point. So yeah, thanks for your attention. And if there are any, I'll be happy to take some questions.
Thank you, Tom. Do we have any questions in the room? Let me check online. So since you mentioned the multi-user in the future work, do you have any idea how you're going to manage the communication and synchronization between multi-users? Is that something you already thought about?
We are massively simplifying this in the sense that we will have this everything synchronous as it is right now, because every single call from Godot to Squeak is going to be synchronous. We have this sort of luxurious position that we can probably adjust simply a spin up to Godot instances, communicating towards the same Squeak instance and sharing the same virtual tree, and just sending events from both Godot instances as they happen for the same callback handlers in Squeak. So compared to all those people who are dealing with high latency issues and the resulting challenges of that, we really have the scenario of essentially 3 systems in the same room communicating synchronously, which makes it obviously a whole lot easier.
All right, thank you. Do we have another question? Okay, Jeremy.
Thank you. Hello. Your code didn't look like it was doing 90 frames a second. Is that an artifact of the video streaming that we're seeing? I mean, did you really get the speeds that you wanted?
Yes, actually. I mean, I can show you briefly, but it sounds like you're not going to see it so well. Actually, I think there's even a tutorial for this. Let me just quickly see. No, there's not. I thought Amit had that. Never mind. I guess then this is not gonna look very believable either, but 3D start. This is now, I believe, 500 objects just flying around in space, and you can probably only see things happening every couple of seconds. But yes, this is running at 90 frames. With one notable exceptions, you have GC stutters a couple of times here, which is something we're still looking into. Obviously, this sort of freedom approach is really costly on the GC end because you're constantly creating these objects for every single frame. Yeah.
So, if there are no other questions, I will have one more. Do you happen to have also some demo where you kind of have a full scene modeled in the thing? I mean, it's nice to have these cubes flying and show the potential in terms of performance, but I'm not really a 3D person, so I don't really know kind of how big a complex scene is compared to the steps.
Yeah, so what I'm showing you right now is the prototype of our VR development environment running in a simulator. So like simulated hardware, because, well, I considered wiring up the system here, but that would have probably destroyed the streaming performance. So you saw this little launcher application, and I'm just putting myself in this little virtual scene, which only purpose really was to allow people to orient themselves better. So this is just visuals. But yeah, we've tried it on a couple of scenes that actually approach these sort of games that we would, for example, build in a game jam. And for that sort of purposes, the system really worked well. We haven't encountered any sort of worst case scenarios here where performance really plummeted in ways we didn't expect.
Okay, so just because I'm curious, how many kind of objects are we seeing here? Is that kind of the 500 you showed before, or is it less?
It's mostly that's mostly static objects. Can actually just briefly check here. So that would be okay. It's actually calculating it. So if you just run the numbers here, I think it's around 200, 300 objects being simultaneously rendered, mostly non-moving. Yeah.
Right. Okay. Thank you very much. Do we have another question? Then let's thanks Tom once more. Thank you.